Hi everyone, I'm Ehsan, and in this presentation I'm going to talk about the application of positive and unlabeled bagging for mineral prospectivity mapping, and I also have a co-author, Dietmar Muller, and would like to acknowledge him for his support during this study. Well, these days we hear a lot about the application of machine learning to integrate different exploration data layers and creating prospectivity maps. But these methods themselves are associated with different challenges and limitations. For example, we know that most of supervised machine learning algorithms require both positive and negative training samples to create a model. And in mineral prospective mapping, we consider known mineral recurrences as positive samples, but on the other hand, they're usually insufficient or unreliable labels for the negative class or barren regions. Different methods have been proposed to address this problem in the past few years, but none of them are that efficient. And recently, a number of efficient machine learning methods have been developed requiring only positive and unlabeled samples instead of negative samples to train the model. Well, these methods are called positive and unlabeled learning or classification methods. And here in this slide, you can see a very simple chart that shows different types of machine learning methods, and we have four major categories called supervised learning, semi-supervised learning, unsupervised learning, and reinforcement learning. And as you can see, positive and unlabeled classification of learning is categorized as a semi-supervised learning method. Well, in real world, the data is often only partially labeled, and that's because labeling data can be expensive or even impossible in some cases. And a common scenario involves having only a small number of labeled samples from the class of interest and a large quantity of unlabeled and unknown data. A classification boundary is still desired in such cases, which differentiates the underlying positive and negative classes. And this problem is known as positive and unlabeled learning problem, or it is also called PUL, and it is of growing importance in machine learning. Fortunately, PUL algorithms exist that can create effective models using low power and memory requirements, and they are able to learn from positive samples and apply what they have learned to relabel unknown samples. And therefore, these methods can be considered a potential solution to a classic challenge that we usually face in mineral prospectivity mapping. And here in this slide on the left side, you can see a standard supervised classification problem in which blue circles are negative samples and red crosses are positive samples, and the black line shows the decision boundary or the classification boundary. And on the right side, you can see a positive and unlabeled classification problem in which black dots are unlabeled samples and red crosses are positive samples. And again, the black line shows the decision boundary or the classification boundary that we have. Well, a few methods have been developed under the category of positive and unlabeled learning, and here in this slide and the next one, I quickly go through two of them, which are two-step approach and weighted approach. In two-step approach, it tries to find probable negative samples from the unlabeled set, and it learns a classifier from the known positive and probable negative samples. For example, here on the right side in this figure, you can see unlabeled samples in black dots, and positive samples are shown in red crosses. And at the first step, using this approach, it specifies the probable negative samples that are usually those that are far from the positive samples, and then it learns a classifier, and based on this classifier, it labels the data. Well, the weighted approach, as it is obvious from its name, it assigns weights to the unlabeled set, and weights represent the likelihood of belonging to the positive class, and it learns a classifier from the known positive and weighted unlabeled samples. And in the figure again, you can see unlabeled samples in black dots, and positive samples are shown in red crosses. And here, using this method, we assign weights to the unlabeled samples, and then it learns a classifier, and based on this classifier, it labels the data. In this study, we evaluated the efficiency of the weighted approach by creating a prospectivity map of IOCG deposits in the Gawler Craton, South Australia, which is the oldest and largest geological province in there, and records a complex geological history spanning from Archean to Mesoproterozoic era. It holds several world-class mineral systems, and is known as an attractive tectonic environment for exploration geologists. In addition to the weighted approach, we used the bagging strategy, which is a parallelized bootstrap algorithm, and it iteratively trains many binary classifiers to discriminate the known positive examples from random subsamples of the unlabeled set and averages their predictions. And in this slide on the left side, you can see the crustal elements of Australia, and the Gawler Craton, the core of the Gawler Craton has been shown using the dashed line on the right side. To create the mineral prospectivity map, we used a big volume of publicly available exploration datasets in vector and raster formats, and they include geological, geochemical, and geophysical datasets, and they were used to generate more than 200 different features, and features highlighted by the model as important can aid in furthering the understanding of mineral systems and formation processes, and to guide future exploration data collection requirements. And here on the right side of this slide, you can see 4 of these data layers that we have used. On the top right, we have the faults that we have in the study area. On the top left, we have the digital elevation model of the study area, and in the lower right, you can see the residual gravity layer, and in the lower left, you can see the radius to pole magnetic intensity. To train our model, we used all the known IOCG and intrusive related mineral occurrences in South Australia, and which are over 1,400, and an equal number of unlabeled samples were generated randomly. And as you can see on the map, the unlabeled samples are uniformly scattered throughout the study area. The positive and unlabeled learning methods can be used as the wrapper of any supervised machine learning algorithm and generate reliable positive and negative samples. In this study, we used the random forest method as the main classifier and compared the results of the standard approach with the combination of random forest and positive and unlabeled learning. And only 50% of the positive samples or minor occurrences and an equal number of randomly selected unknown data points were used to explore how well the model training works. And we can categorize the whole data points into three classes. One is the unlabeled samples, the other one is unlabeled positive samples and positive samples. And we have hidden the unlabeled positive samples from the machine and trained that using the rest of the data points. And our evaluation metrics to assess the classification performance include standard statistical measures like precision, recall, accuracy, F1 score, and AUC score. Well, here in this slide, you can see the result of applying standard random forest to generate a prospective map of IOCG and intrusive related mineralization. As mentioned before, we trained our model using known mineral occurrences throughout South Australia and also randomly generated negative samples. And we created the probability map for a small portion of South Australia, which is located in the east of the core of the Golden Craton as well. And this region involves the giant Olympic Dam deposit as well. And on the right side, you can see the high resolution probability map of the region. And here are the results of applying the combination of random forest and the weighted approach to generate the prospective map of IOCG and intrusive related deposits. As you can see, compared to the previous map, the mineral occurrences are well correlated with high probability values. And from the geological perspective, we observed that the high probability values or anomalous regions are well correlated with intrusive related units, and their ages actually range from Archean to Mesoproterozoic. And here in this table, you can see the performance metrics of both methods. And as can be seen, 4 out of 5 metrics of the positive and unlabeled bagging method outperforms the standard random forest. And we actually retain 50% of positive samples from training, and still you can see we have achieved an accuracy of nearly 90% using the weighted approach, which is pretty good. And on the right side, actually the graph on the right side shows the percent of positive samples correctly classified after hiding different fractions of positive samples. And again, in this graph, you can see the higher performance of positive and unlabeled bagging compared to standard classifier. Okay, to summarize, well, we applied a positive and unlabeled learning method called weighted approach to create a mineral prospective map of IOCG and intrusive related copper in the Golden Craton in South Australia, and we used various exploration datasets to create different features, including geological, geochemical, and geophysical data. And we used known mineral occurrences as positive samples and created different sets of random samples throughout the study areas, unlabeled samples, and based on the different evaluation metrics, the performance of the model is stable, which is an important factor in machine learning projects. And it shows the reproducibility of the results. And based on the results, the positive and unlabeled learning method improves the accuracy of the maps on average by nearly 10%, and the prospectivity map shows a strong spatial correlation between high probability values and known mineral occurrences, and even predicts potential regions with few or known mineral occurrences that can guide, future exploration. And here are the main references that we have used in this study, and the results are going to be published in a journal paper soon, and along with the paper, we are going to release a software tool that enables the users and readers to reproduce the results and also apply the positive and unlabeled learning method to their study areas. And here is also my email address, and feel free to contact me if you have any questions. And thank you all for listening.